Okay, so last day we have been talking about the frequency response characteristics of amplifier, BJT based amplifier, and we have discussed one such effect which is known as a Miller effect, right? And in that case, we have discussed about the frequency response characteristics of a common emitter amplifier, and then the common base amplifier, and then the common emitter common base cascade, which is also known as a cascade amplifier. And you have noticed that whenever we use this common emitter common base cascade, a cascade amplifier, that particular amplifier will give you a moderate gain with moderate bandwidth that you cannot get using a single isolated common emitter or isolated common base amplifier. So that time I have told you that, in fact, you can also remember that we have actually we did not go for this extensive calculation. We have identified some input RC circuit, identified some output RC circuit, and from that you have found out the value for this higher cutoff frequency, f of h. Now here, in this particular slide, the circuit for a common collector amplifier has been shown. Common collector and emitter follower, right? The collector is connected to this power supply, that means AC ground. And if you just follow this analysis, this calculation and all, this is once again very brute force kind of thing. That means we have drawn a small signal model using all those capacitors and all, current source and your resistances and all. And then we have done some extensive mathematical calculations using KCL, KVL, right? That means the approach that we have taken last day, this approach is completely different, right? But then you will realize that we can also do this calculation. That calculation can also be carried out if we just invoke the concept that we have learned last. We'll discuss this in detail. Anyway, so to start with, hopefully you can identify that this is a common collector amplifier, which is having a very simplest kind of biasing arrangement. Only RB is there for providing the corresponding base current, and the input is applied at the base with signal source resistance RS. This coupling capacitor is there, but as I told you last day, in this class or last day also we have mentioned the effect of internal capacitors. The effect of the external capacitors like coupling capacitor, bypass capacitor, load capacitor will be discussed in the next part. So for the timing, let's assume this coupling capacitor will provide almost zero reactance, right? And this is your output terminal from the emitter terminal, and this one is your output resistance, that is RE. Now, already you have encountered this small signal model for common collector amplifier or emitter follower. So same thing, only the inclusion of two internal parameters, internal capacitors. One is the CPi, second one is the CMU, right? So notice here, this one is Vs, signal source with the signal's resistance Rs, and you have this RB connected from the base terminal to the ground terminal, AC ground, right? So this is your base terminal. Between base to emitter, you have this Rpi, and then from collector to emitter, you have this GMV and collector to emitter, you have this R. At this time, this collector is at AC ground because collector is connected to your supply, right? That is AC ground. And then from emitter to ground, you have this RE, that resistance. So that part is okay. We have already encountered this one last time also. And we have included two internal capacitors there. One is CPi, second one is CMU. CPi is connected between the base and emitter, and CMU is connected between base and collector, right? Now for the timing, let's forget about any Miller effect. Forget about any Miller effect, and let's attack the circuit from your understanding, from your knowledge in your circuit theory, right? So what I have done over there, so I have just drawn the same circuit, but upside down, something like this. You have this Vs, this Rs, this Rb. That's fine. What else? You can notice that CMU is connected between base to AC ground, right? Base to AC ground, we have CMU, this one. Base to AC ground because collector is AC ground. So base to AC ground, we have this CMU. Then Rpi is there between base to emitter. You have this Rpi. And then CPi is there between base to emitter because Rpi and CPi, they are in parallel. So you have this Rpi CPi combination. And this is your emitter terminal, the output terminal. What else? You have got like this. Now you just observe over there. You have this RE. RE is connected between emitter and AC ground. R0 is also connected between emitter and AC ground. So I can consider that RE and R0 in parallel. So this is RE parallel R0, this resistance between the emitter and the AC ground. So this is your AC ground. And then what else? This GMV is there from collector to emitter, right? So actually, I think, yeah. So this direction is, yeah, this direction is opposite, should be opposite, yeah. This one, this should be the direction for this current source. from the emitter to from this ground to emitter or collector to emitter upward. Okay, so this is your circuit diagram, I mean the modified circuit diagram. And let's assume that over here, let's assume that as you understand, this voltage is the base voltage over here at the base terminal, and the current being drawn, say let it be IB, and then the impedance as perceived by this circuit, input impedance over there, suppose this is ZB, looking at this point. So here the voltage is at this terminal, the voltage is VB, the current being drawn is IB, so VB upon IB will give you the expression for the input impedance ZB. So we have already encountered this ZB, or rather RB, rather Rin for a common collector amplifier when these capacitors were absent. Right, so this time we will also encounter these capacitors, and that's why it is known as ZB, the impedance. So for doing this, what I can go for, yeah. So now you just check over there these calculations, whether these are perfect or not. So what is your V out? So as it was mentioned, this is, I mean, this direction is opposite. So from here to here. So what is the current that is flowing through this RE parallel R naught? This current is IB over there. This current is IB. IB is flowing through this combination, R pi C pi combination, right? R pi C pi combination. So I can call it like let it be Z pi. Let me call this as Z pi. So Z pi is basically the R pi and C pi. C pi means what? 1 by SC pi. C pi is a capacitor. So what about your impedance? That is 1 upon SC pi. So R pi and parallel to 1 upon SC pi, that will give you Z pi. Okay. And if I just consider the admittance, this admittance Y pi is given by this one. Y pi is given by 1 upon Z pi, that is 1 by R pi plus SC pi. Two admittances are in series. Impedances are in parallel. I mean the resistances are impedances are in parallel. Okay. So fine. And then what about V out? V out is what is the total current flowing through this? This current is IB. This current is IB. This current is GMP pi. So if I apply KCL at this particular node, the current that is flowing through this RE parallel R naught. So that is nothing but IB plus GMP pi, right? Now this current IB plus, because the direction is opposite. Direction is opposite. So both of them are entering through this. So this IB plus GMP pi is flowing through this, and so V out is IB plus GMP pi multiplied with RE parallel R naught. And you can remember that for a common collector amplifier there is no such phase difference, right? So that's why IB plus GMP pi times RE parallel R naught. And VB and V pi, they are also related. So how can I write VB and V pi? So this is this voltage is VB over there. So this is basically V pi plus V out, right? So VB is equal to V pi plus V out, right? So then what I can observe. So ZB, as you know, ZB is nothing but VB upon IB. So if you just substitute all those values, then ultimately what you are getting, ZB in this particular form, Z pi into 1 plus GM RE parallel R naught plus RE parallel R naught. So I can call this RE, I can give a name to RE parallel R naught, let it be RE dashed, RE prime, right? So what is your ZB then? So ZB, if I call that RE parallel R naught is your RE prime, this one, RE parallel R naught is equal to RE prime, then ZB is given by, your Z pi is already there. So what is your Z pi? Z pi, as you know, Z pi is nothing but 1 upon Y pi. So 1 upon Y pi, that is expression for Y pi, 1 upon R pi plus SC pi, multiplied with 1 plus GM RE dashed plus RE dashed, right? Is it okay? Clear? So then now we can also simplify this expression. We can also write the same expression. The same expression can also be written in this particular form. Now, what is the importance of having the expression in this particular form? Now, the same expression is written like this: RE prime is there plus RE pi, or RE prime, this one, and then this expression can be written as, this entire expression can be written as in this particular form. So what is that? This is basically the summation. What is this? 1 upon R pi into 1 plus GM RE prime. So this is basically a resistance. Denominator is resistance. This also another resistance. This denominator, if I consider 1 plus GM RE prime by SC pi. Right? So the summation of two, what is this? Summation of two admittances. summation of two admittances, and then 1 upon this. So ultimately it will be an impedance in that particular form. So what is the necessity of writing in that particular form? So Z, that is nothing but a ZB, right? ZB, that is given by 1 admittance plus another admittance. 1 upon Y1 plus Y2. So if I call this as Y1, if this is your Y1, suppose this is your Y1, I can call it Y of 1, and this can be Y of 2. Y of 1 and Y of 2. So Y1 plus Y2, 1 upon this. So two admittances are in parallel condition. That's why the admittances are added together. 1 upon Y1 plus Y2. Plus you have something Re prime. Right. So therefore, since ZB can be represented in that particular form, so therefore I can modify my expression. Now I can modify this expression, or rather a small signal model, in this way. Remember, you have got this expression, that one you have this R pi, you have this C pi in parallel, then Re prime and GM P pi. These two are in parallel. You have one parallel combination there, R pi C pi, and then another parallel combination over there, and these two are in series. And that is basically giving you the flavor of ZB, because this voltage is VB and here the current is IB, and the ratio of these two VB upon IB will give you ZB. So what is ZB basically? So we have done this calculation to some extent, and then we have noticed that this can be represented as 1 upon some Y1 plus Y2 plus something, some Re prime, right? So therefore, so this part of the circuit can be modified. This part of the circuit can be modified, and then ultimately what we are getting is this one. Now check whether this is justified or not. What I have told you, this is basically this Re pi into 1 plus GMR is basically one resistance, and this is another resistance, 1 plus GMR prime by SC pi, right? These two are added, 1 upon this plus 1 upon this, they are added. That means they are in parallel, and this entire thing is in series with another resistance. So therefore, what about this resistance? What are those two resistances which are in parallel? One is obviously R pi into 1 plus GMR prime. What about the other? This is not a resistance. This is basically a capacitance, right? The second part is the capacitance. That will give you the notion of a capacitance, because you have this SC pi terms. So what is that capacitance? This is nothing but, what is the value of this capacitor? This C pi upon 1 plus GM Re dashed, right? So these two elements, so this impedance and this impedance, these two are in parallel. So therefore their admittances are in series. So that's why 1 upon this plus 1 upon this. Total admittance, right? Y1 plus Y2. 1 upon this will give you the total impedance. This, that means impedance of this, and this entire thing is in series with Re prime, right? Now, what is the reason that I have represented that particular thing in this form? Because life was good without this without this representation. So there must be some specific reason, and that is what I would like to concentrate right at this moment. Because this calculation, while you perform this calculation, you are not bothered about this Miller effect. What we have done, we have just drawn the small signal model, and then you have simply gone for this brute force calculation, KCL, KVL and all these things, and then you have come to this. The point is that you have to identify whether any Miller effect still exists for this circuit or not. Yes or no, you have to check, right? Because hopefully there is something in your mind, I don't know whether some bell is ringing in your mind or not, that this particular parameter, this 1 plus GM Re prime and 1 plus GM Re prime, either it's multiplied or it's divided. Last day, hopefully you can remember, there is something like 1 minus A, right? Z by 1 minus A, right? Something. So Miller effect will give you something 1 minus A parameter, 1 minus A term. So this term is 1 plus GM Re prime, this term is 1 plus GM Re prime. So let's have a look once again. Is there any effect? So just by observing this circuit, you might feel that there is a kind of Miller effect. There could have been some elements which are experiencing Miller effect. So we have to establish this one once again. So now once again, let's go back to the original circuit. This one is blue, which has been represented by this, drawn by this blue color. Now, what is your input terminal here for a common collector? What is your input terminal? Base. Base is your input. What is the output terminal? Emitter. Emitter. So this is your input terminal. This is your input terminal. This one. This is your output terminal, right? So is there any element between these two?
C pi, R pi.
You have C pi, you have R pi. So these two elements, so this R pi and C pi, they are basically making a connection between the input and the output for this common collector. For common emitter, you have seen that element was C mu. C mu was there, which is making a connection, a bridge between the emitter and between your input and output, between the base and the collector. And here, base is the input and the emitter is the output, and between the base and the emitter, you have this R pi, C pi. They are basically, they will experience the Miller effect, right? Now, if I once again I can just tell you the expression for the voltage gain. Yeah, that part is good. Can you remember the expression for the voltage gain for a common collector amplifier?
Less than 1.
Is less than 1, right? So the voltage gain expression AV. No, there is no negative sign. Actually, the expression was something like this. Yes, it was like 1 plus beta times Re parallel R naught divided by R pi plus 1 plus beta Re parallel R naught. Apart from that, you have some coupling loss in the form of Ri by Rs plus Ri. So forget about this part. Only just focus on this one. 1 plus beta times Re parallel R naught divided by R pi plus 1 plus beta times Re parallel R naught. So I can call your Re parallel R naught is nothing but your Re prime here, right? So I can call this as 1 plus beta times Re prime divided by R pi 1 plus beta times Re prime. That is the expression for AV, right? And lastly, you have noticed that whenever we encounter the Miller effect, the impedance looking from the input side, that is Z in is equal to Z actual impedance divided by 1 minus A, right? So this is your expression for A. This is the expression for the voltage gain. So what will be your 1 minus AV? What is 1 minus AV? What is that? Once again, you have this R pi plus 1 plus beta times Re prime in the denominator. The numerator, you have this R pi plus 1 plus beta times Re prime minus 1 plus beta times Re prime. So you are left with only R pi, right? Is it okay? So what is that? So I can this one. This is 1 minus AV. So that can be approximated to R pi. Since beta is very large, so I can call it like R pi plus beta times Re prime. Can I do it? Since beta is large, 1 plus beta can be approximated to beta. So can this be simplified? Again, what is beta? What is beta?
Forward.
No, that's fine. So what is the relation between beta and R pi? Is the relation? GM. Right? So now if I divide it by R pi, if I divide the numerator and denominator by R pi, what is that? It's basically 1 by 1 plus GM RD dashed. Right? So 1 minus AV is coming out to be 1 by 1 plus GM RD prime. 1 by 1 plus GM RD prime, approximately 1 by 1 plus GM RD prime. That is 1 minus AV. Okay. So what will be the new impedance? If you have some Z between the input and the output, the input side, what is the effect of this Z? This is nothing but Z by 1 minus A. So Z by this 1 minus AV. So if you have some, so now you have this kind of thing. You have this resistance, this R pi, you have this capacitor C pi. This is your base terminal, this is the emitter terminal, and between these two terminals you have the input and the output. So now if I want to decompose, right, at the input side between base to ground, what will be that? What is the effect of this? You have this R pi divided by 1 minus A. R pi divided by 1 minus A. So what is that? R pi divided by 1 plus GM RD prime. That means R pi into 1 plus GM RD prime. What will be the C pi then? C pi will be C pi by 1 minus GM RE prime. Okay, so that is the basic calculation behind this. So what you have got out of these calculations using your KCL and KVL, eventually this is coming from the notion of the Miller effect. The same thing. Okay, so here this R pi capacitor, R pi and C pi, both of them, they are experiencing the Miller effect. Now once again, okay, that is the thing. So now, okay, fine. So I can simplify the circuit like this. Now, is it similar? What do you feel? Is it similar? Is it similar to what I last time? Anyway, what is your output? So, okay, I'm coming to that. What is your output expression? So, output, you know, this output is taken from which terminal? Output is taken from emitter terminal. So, basically, here you have this total current. Once again, if I just go back, this output is taken from this terminal V out, right? So what is that? So this can be represented, output can be represented as the total current is IB plus GM pi, as you already observed, IB plus GM pi multiplied with RE prime. So if you just represent IB as V pi into Y pi, where Y pi is the admittance over there, then V out is equal to V pi into Y pi plus GM times RE prime. So I don't know whether you have got some idea about the zero and the pole of in transfer function. You have got this idea. That's great. You have got this idea. That's great. So what I find, so what they are V out upon V pi, you have Y pi plus GM expression, right? And remember this Y pi plus GM, that expression involves some frequency dependent element, because Y pi involves some S dependent elements. What is Y pi? You have already observed. This Y pi is given by 1 by R pi plus SC pi, and accordingly you have plus GM there. So 1 by R pi plus SC pi plus GM is equal to 0. And if you just simply substitute all those values, then ultimately what I am getting, this 1 plus S into R pi C pi, this one by 1 plus beta is equal to 0. Okay. So this time, last time, remember, hopefully you can remember, the last time in our expression for the voltage gain from, VOS upon VOS by VIS, you have something like this, if you can remember it properly, some constant K divided by 1 plus S tau, right? That time I told you that, okay, there is something, this S parameter was there in the denominator, there was nothing in the numerator. In the numerator you have a constant term, the denominator you have some S dependent. So there was no such zeros, you have only one poles. First order system, only one pole. But here, what I find, I am just observing this inputs, I am just observing this numerator part over there. So V out upon V pi, you have this Y pi plus GM times RE prime. And this Y pi plus GM, that involves some S dependent parameter, and over there you have 1 plus this entire thing, that is equal to 0, and that is coming in the numerator part, because this is nothing but your V out upon V pi, and you can represent V pi in terms of V in also, or Vs also, you can represent. So therefore, you have this 1 plus S into R pi C pi by 1 plus beta is equal to 0, from where you can identify the 0 occurs at a frequency of F naught. What is that F naught? As you know, this S is equal to, last time I told you, what is that S? This S can be represented as J omega, right? So what I can write, 1 plus J capital omega, that is the analog frequency R pi C pi by 1 plus beta, that is equal to 0, right? So from here I can find that my 0 frequency is occurring at 1 by twice pi into R pi by 1 plus beta multiplied with C pi, this one. This is the frequency, 1 by twice pi R pi C pi upon 1 plus beta. That is the 0 frequency. That means at that particular frequency, your frequency response will become 0. Right? So now for typical values, let's now take some typical values, and let's take some typical values, and let's consider R pi to be 5 kilo ohm, C pi 11 picofarad, beta 100. Then F naught is coming out to be 290 megahertz. F naught. That means at F naught at frequency 290 megahertz, the 0 frequency will occur. That means the frequency response drops to 0 at 290 megahertz. Okay. Apart from that, this particular circuit, this common collector thing, can also encounter some other the pole frequencies as well. So let's check. So how to check the pole frequency? Yes. So for that we will not do this calculation, this extensive calculation. Rather, we will go for this input RC circuit, and from that we will find out the higher cutoff frequency. Okay. What is that? How does it look like? This is the circuit, no? This is the circuit. What I get? This one is in parallel R pi plus 1 plus GM RE prime. This is in parallel with C pi by 1 plus GM RE prime. Okay, and that is typically large with respect to RE prime. Why? Why typically large? Because here, if you just observe over here, RE prime is what? R not parallel RE. RE prime is R not parallel RE. It is essentially governed by RE, right? And here, what you have? Here you have this R pi gets multiplied with some GM RE. So obviously this one is larger as compared to this RE prime, right? So this entire thing is coming in series with this RE prime, which is typically small as compared to this entire thing, right? So therefore, I can consider, okay, this is negligible with respect to this particular parallel combination. That will make our analysis even more simpler, right? Now, if I assume this one, then ultimately, hopefully you can identify the circuit with which you are familiar. Last day also we have got this circuit. What was that? You have got this one, this Vs over there, this circuit. You have this resistance over there in the form of Rs. You have this resistance over there in the form of Rb. You have this capacitor over there in the form of C mu, and you have this resistance is there in the form of R pi into 1 plus GM RE prime, and you have another capacitor. Let me just this part, yeah, and you have another capacitor over there, and this value is C pi by 1 plus GM RE prime, right? Is it a well-known circuit? Is it a familiar circuit? Last day, hopefully you can remember the circuit like this, no? Last day I have noticed, no, this kind of circuit.
Yes.
And so now, if I do this approximation that RE prime is neglected with respect to this combination, then hopefully it's great. It's great. You have these two capacitors. Sorry, you have these two capacitors. These two capacitors are there. So what I can do? Okay, let me just simplify like this. You have only one capacitor whose value is given by, you have C mu plus C pi by 1 plus GM RE prime, right? And these two resistances RB and R pi into 1 plus GM RE prime, they are in parallel, so you can find out the parallel combination that will give you RP value. Eventually that was your RP, that was RS, and this is CP. So same form, RS, RP, CP. Okay, so then if you just consider over there, so what is your effective time constant? This RS RP parallel combination, right? So what is RS? RS is the source resistance over there, and RP in the form of RP, you have RB and R pi into 1 plus GM RE prime, and then these two capacitors are in parallel, so their effective value will be the summation C mu plus C pi by this. Then ultimately, if you do this calculation, then ultimately with those typical values, it is coming out to be, okay, it is 1500 megahertz. That is pretty large, right? So the basic idea of this discussion is that if I have this common collector amplifier, typically you know that common collector amplifier is the last element of any transmitter circuit, because for this the input is very large, output resistance is very small, so that whenever you have to connect your output to some very low resistive load, like for example a loudspeaker, for example, whose resistance is in the order of few tens of ohms. In that case, you cannot directly connect the common emitter on the common base amplifier. So that's why this common collector is typically used as the last element of an audio amplifier. The last element is your Common collector amplifier. So what I observed was there that this common collector doesn't, this higher cutoff frequency or the zero frequency that is pretty large. Higher cutoff frequency 150, 1500 megahertz. The zero frequency occurs as 290 megahertz. So obviously this will not interfere with the operation of your common emitter, common base, which are present in the preceding stages of amplification. So common collector will not do any harm for your applications. That is the entire observations from this calculation. Okay. So we have discussed the effect of the internal capacitors, the Cpi and Cmu for common emitter, for common base, and for common collector amplifier. And we have also noticed that if I combine this common emitter, common base in the form of a cascade amplifier, then obviously it will give you some advantages out of each of these two types of amplification. Okay. Now let's move to the external capacitors. Already noticed that there are few external capacitors. One is your coupling capacitor, then your bypass capacitor, and then the load capacitor. Load capacitor you can also have at the load circuit in any amplifier. So essentially, if I observe the effect of, so to summarize the observations that we have made as of now, these internal capacitors. So typically, what is the behavior of those internal capacitors? Typically, they will give you the notion of a low frequency response. The response is something like this. So the response is something like this. If the frequency varies, and if this is your gain, then for internal capacitors, this is the response. Typically, this is the response. Now, this particular frequency, hopefully you can remember, this frequency is known as the higher cutoff frequency, FH. We call it FH, higher cutoff frequency. So what is that? This is the frequency. So over here, this value is almost constant, right? And a point will come in the frequency axis where if it is constant, that means it is at 0 dB, and a point will come in the frequency axis when it drops to 3 dB, and that marks the end of this pass band for a low pass filter, And we have identified the FH value for different types of amplifier, like for got some FH, for common base you have got another FH, for common collector you have got another FH, so different values of FH. But eventually all of them, the circuit is something like this. The input and as well as the output RC circuit is something like this. And this circuit is nothing but a circuit for a low pass response. Hopefully you have studied this in your circuit theory course. If I have R and C in this particular fashion, that means R in the series path and you are taking the output from this is basically a low pass response, right? And on the other hand, if I just consider the other way around, that means the capacitor is there in this path and resistance there in this path, then it will give you the notion of a high pass response, right? And we'll look into this thing over here. As of now, both of them, all these two capacitors, internal capacitors, Cpi and Cmu, for common emitter, common base, common collector, they are giving you the flavor of a low pass response. And accordingly, you have to identify what is the higher cutoff frequency. That higher cutoff frequency is obtained like sometimes 20 megahertz, sometimes 35 megahertz, sometimes 200 megahertz, sometimes 1500 megahertz, right? But the response is something like this. Response is like this. The low pass response. Okay. Now let's move to the internal, the external capacitors. So our journey with the internal capacitor is over. Now let's move to the external capacitor. So to start with, let's consider the coupling capacitor. Now while doing this analysis for external capacitor, this time we'll assume that the effect of the internal capacitor is absent. Right. So typically the effect of this internal capacitor is observed at very high frequency, isn't it? Because you have noticed that 20 megahertz, 35 megahertz, 200 megahertz, 1500 megahertz. So typically at that particular frequency you have the higher cutoff frequency or the zero frequency at those higher values, not in the range of few tens of hertz or hundreds of hertz or kilohertz or hundreds of kilohertz or tens of kilohertz. Typically it's in the range of megahertz, right? And at that particular frequency, since the coupling capacitor was there in the series path, so we assume that the coupling capacitor will provide you very insignificantly small reactance value, because as you understand, what is the reactance provided by any capacitor? 1 by j omega c, that is the reactance. Now whenever we observe the effect of those capacitors, those internal capacitors, your Cpi and Cmu, typically this is the frequency is very large in the range of megahertz. So if this omega is very large, then this 1 by j omega is very small. So if some capacitor is there in the series path like so, so at those high frequencies in the range of megahertz, you can simply neglect those capacitors. So that's why we have just neglected those this internal capacitors, like this coupling capacitors in our previous analysis, right? And while doing this, you will see that these capacitors are very much pertinent at low frequency operations. Obviously, yes, because this is in the series path. This capacitor is in the series path. In the signal is applied over there, and this is in the series path. So therefore, this capacitor will play a very vital role whenever the operating frequency is small enough. When omega is small, then this reactance will be, or impedance will be large. And at that frequency, when the frequency operation is small enough, then those capacitors like C pi and C mu, they become irrelevant. Right? So at very low frequency, only I have to observe the effect of these capacitors, coupling capacitors, the external capacitors, which are there in the series path. Okay, so while doing this analysis, the effect of external capacitors, we will just forget about the effect of the internal capacitors, because internal capacitors are vital in high frequency operations, while these external capacitors are typically vital in the low frequency operations. Okay. Anyway, so here what I find, this is the small signal model for already you know this one. So this circuit I'm not repeating this one once again. This is well known. This R pi, you have this GMP pi, you have this RE, you have this R1 parallel R2, RS. So everything was already you know this one, right? The addition of CC, that is a coupling capacitor, is a new thing over here. Addition of CC, this coupling capacitor. Last time in our discussion on the small signal amplifiers, we have just got rid of this CC. So CC was not there. Actually, we have a short circuit path, because that time I assumed that my signal frequency is large enough so that CC can be neglected, or the effect can be neglected. But this time I'm allowing my signal frequency to vary from very low frequency in the range of tens of hertz to say few kilohertz. At very high frequency, kilohertz, tens of kilohertz, hundreds of kilohertz, CC can be neglected. But at very low frequency, in the range of tens of hertz, neglect the effect of this coupling capacity, CC. Anyway, so if I just once again do this calculation, so yes, so this current, this is the total current II that is being supplied by the signal source. This is nothing but the voltage, that is Vs, upon the total impedance. So what is the total impedance over there? Suppose this is RS is given. This is CC. So accordingly, 1 upon SCC will be the reactance provided by this capacitor. And then looking at this point, if this resistance is Ri, then this is Rs plus 1 upon SCC plus Ri. Right? And suppose looking at this point, this impedance is, suppose this resistance is Rib. And what is Rib? You have already calculated this Rib. This Rib is nothing but R pi into 1 plus beta times R. Just refer back to our discussion what we have made last time. This Rib, looking at this point, this resistance is given by R pi plus 1 plus beta times R. Right? And then this Ri is nothing but R1 parallel R2 parallel Rib. Okay? Okay, fine. And then what is your V out? V out is minus GM V pi times this RC. Right? And what is your V pi? V pi is nothing but IV times R pi. IV is the current which is flowing through this, and across this R pi, the voltage developed is V pi. So IV times R pi is equal to your V pi. So accordingly, if you just simply substitute those values, then what we are getting is this one. V out is equal to minus beta RC times this one, R1 parallel R2 upon R1 parallel R2 plus RIB, multiplied with this factor. Now this factor is of our interest right at this moment, because already you know that this one is basically frequency independent parameter. You have beta, RC, R1 parallel R2, all of them are resistors. Now here this parameter, this particular thing, in fact the denominator, this is a function of frequency. Right, so we have to observe what is the effect of this. So okay, so the small signal voltage gain as a function of frequency can be represented as this minus beta RC times R1 parallel R2 upon R1 parallel R2 plus RIB multiplied with this one, 1 upon RS plus 1 upon SCC plus RI. So now, what is that? Now if you simplify this one, plus Ri plus 1 upon SCC, to simplify this part, you are getting like SCC upon 1 plus RS plus RI times SCC. So it is in which form? Is it in the form of K by 1 plus or 1 by 1 plus S tau? No. It is in that particular form. It is in the form S tau by 1 plus S tau in this particular form. And remember, this is not S, I mean, both of them are tau over there. By tau, I am coming to that. It's basically S tau by 1 plus S tau. K into S tau by 1 plus S tau. What is that tau? What is that tau? Tau is equal to RS plus RI into CC. So what is your AV j omega? At any frequency, angular frequency j omega, what is that? Although I have written over there using a small omega, but remember this small omega stands for the digital frequency and the capital omega stands for the analog frequency. Anyway, you can also make it like capital omega. No harm. Because as of now, you don't have an idea about the digital frequency and analog frequency. That's why this omega is omega. But remember, whenever you study this DSP and all, then the analog frequency is capital omega. This is called capital omega, analog frequency. And this is a small omega. Small omega stands for the digital frequency. Anyway, you can also use capital omega or small omega. No harm done. So what is that? This APJ omega. A mod of this is basically mod k omega tau divided by root over 1 plus omega tau whole square. So you can represent this omega in terms of twice by f tau square root of 1 plus twice by f tau whole square. Okay. So now we will represent this in the logarithmic scale. Logarithmic scale. Why logarithmic scale? Why log is important? Sometimes whenever the range of your input is very large, suppose from say 0 or say fractional value to say 1000. Suppose your minimum value is equal to say 0.5 and the maximum value equal to say 5000 or 500. So say minimum value is equal to say 10 Hz, maximum value equal to say 10 megahertz or 100 megahertz. So is it possible for you to represent this entire thing on a linear graph paper? It's not possible. So therefore, whenever you have some variations like this from few tens to say 10 to the power 6, the order difference, 5 order 6 order difference, and it is not possible for anyone to represent the same thing in a linear graph paper. So then we have to take the help of the logarithmic graph paper. Now, if one side is logarithmic, then it is known as the semi-log. If both sides are logarithmic, then it is known as the log graph paper. Log or semi-log. Okay. Anyway, so what I find over there, typically what I find, so for logarithmic part, so you have to take the log, both sides, you have to take the log. So you take log, so you have, you know the formula log m into n, that is log m plus log n. If you have multiplication, this is basically added, right? So you have log mod k plus log twice by f tau, and then this minus, because this is there in the denominator, minus log of square root of 1 plus 4 pi square f square tau square. Right? And when you take the log and if you multiply this log value using 20, it is known as the decibel value. dB value, right? So AV j omega in dB is given by 20 log mod k plus 20 log twice by f tau minus 20 log square root of this entire thing. Right? If you only take the ratio of the voltage gain, it will be 20 log. If you take the power part, then you have to take 10 log. Power part. Because here I have taken only the voltage gain part, not the power gain. 10 log. Okay. Okay, fine. What I get typically, okay, I am coming to that. Before that, we would like to draw this variation. How does it vary? You have basically 3 parameters. Now it is more complicated. It's not like your k by 1 plus s tau. Rather, k into something s tau by 1 plus s tau in that particular form. Okay. So therefore, what I need to do to observe the effect of each of these parameters. So here in the logarithmic scale, we have this AV j omega. If I consider this AV j omega, here you have 3 different components. This 20 log mod k plus 20 log twice by f tau minus 20 log square root of this entire thing. And the effect of each of these parameters, each of these terms on frequency, we have to observe. Okay. So first of all, you just take a look at this effect of this AV j omega dB. Whenever I just consider the first parameter, that is 20 log mod k. What is k here? K is a constant. K is not a function of frequency. So as you change the frequency, as you change the frequency over here, so as you change the frequency, this is 20 log mod k. It's not a function of frequency. It will be constant throughout. Constant. It's not a function of frequency. What about the other part? 20 log twice by f tau. As you change the frequency, what will be the impact? How does it vary? Forget of this 20 part, just concentrate on log twice by f. Only concentrate on this part. Log of twice by f tau. Okay, it will vary with frequency, but how does it vary? How does it vary? That means now there are some notations for this. Suppose you have got some frequency. Suppose your frequency operation is equal to say, let it be say 100 hertz. Now if I make it from 100 to 200, 100 to 200, what is the change in the dB scale? 100 to 200, or 200 to 400, or 400 to 800. That means if I double the frequency, so 2 pi f tau is there. Now if the frequency is say, suppose let me have two numbers. One number is A1. A1 is equal to, say, let it be 20 log of twice pi f1 tau, and A2 that is equal to say 20 log of 2 pi f2 tau, where f2 is equal to twice f1. That means I increase the frequency by a factor of 2. Okay. So how can I write this A2 in form of in terms of A1? So this A2 is equal to 20 logs, forget of the 20, log of 2 pi f tau, f2 tau. So f2 is nothing but 2 f1. So I can take this 2 part outside. So what is log 2? You just calculate what is log 2? 0. 0.3, right? 0.3.
Not to 0.69.
0.302 or something like 0.3, approximately 0.3, right? Then the rest part is the same. So therefore, what I find that if the frequency is magnified by a factor of 2, then your A2 is becoming how much?
Plus log 2.
It is becoming how much?
A1 plus log 2.
Yes. So A1 plus 20 log, right? A1 plus 6 in dB. So all of them are in dB. 20 into 0.3, 20 to 0.3, that is 6. So that means if I increase the frequency by a factor of 2, the corresponding dB value will increase by an amount of 6. Right? So it is known as 6 dB per octave. The gain is 6 dB per octave. Okay. On the other hand, suppose let's take another consideration. Now, say for example, let's make suppose your f2 is equal to say let it be 10 f1. That means I increase the frequency by a factor of 10. By a factor of 10, not by a factor of 2, rather by a factor of 10. Say for example, from 100 Hz to 1 kHz, 1 kHz to 10 kHz, 10 kHz to say 100 kHz, like this. Then what will happen over there? Your A2, new A2 will be how much? A2 will be A1 plus how much?
20 log 10.
Huh?
20 log 10.
20 log 10. Log 10 means 1. That is 20, right? 20 in dB. Right? That means 20 dB per decade. Same thing. Either you call it like 6 dB per octave or 20 dB per decade. Same thing. Either it is called 6 dB per octave or 20 dB per decade. Same thing. That means if I change the frequency by a factor of 2, the corresponding dB value will increase by A2 is equal to A1 plus 6. Right? Or A2 is equal to A1 plus 20 if I increase by a factor of 10. Okay? So essentially it's a straight line with that particular slope 6 dB per octave or 20 dB per decade. Okay, that's great. And then apart from that, if I just once again take a look at this expression 20 log twice by f tau. Now when this twice by f tau, this factor is becoming 1, then what will be 20 log this? That will be 0. And that is coming at what? At which frequency? When the frequency is equal to 1 by twice by tau. So when it is 1 by twice by tau, then it is crossing the zero point over there, right? And this is the change. This is the change. 6 dB per octave or 20 dB per decade. Clear? So that is coming from this part, second part. While the first part is constant, it is not a function of frequency. This is constant. Second part will increase by 6 dB per octave or 20 dB per decade. Whatever the third part. Third part is a little bit complicated. Now you have 20 square root of something, 1 plus 4 pi square and all. Now then you can have two types of approximations. So one approximation when your this twice by f tau, this parameter is much less as compared to 1. Much less. That means you can neglect this one. So then it is only 20 log 1. That is 0. When this frequency is very small, then it is almost 0. Right? When this twice by f tau, this part is much less as compared to unity. Then on the other hand, if this twice by f tau is much greater than unity, there is another part, two extreme points. When this is much greater than 1, then this will dominate. You have only 20 log twice by f tau whole square and square root of this. So almost 20 log twice by f tau, that means this almost equal to the the second element. 20 log twice by f tau with a minus. That means this time the slope is negative with a minus 6 dB per octave or minus 20 dB per decade. Right? And then at frequency, so when your twice by f tau, when this value is equal to 1, when this one is equal to 1, exactly equal to 1, then it is 20 log of root 2. That is how much? Minus 3. 20 log root is minus 3. That means at f is equal to 1 by 2, twice by tau, this is 3 dB less as compared to the zero frequency gain. Okay. So now we have three components. First component is this one, which is not a function of frequency. Second component will increase by factor of, second component will increase by 6 dB per octave or 20 dB per decade. And the third component is something like this. Now, what is your overall frequency response? This is basically the summation. So you have to add this different. This one is graph 1 plus graph 2 plus graph 3. Then can you tell me how does it look like if I add them for a wide range of frequency from 0 to this? Just take a look at very high frequency. At very high frequency, this plus and this minus gets cancelled. At very high frequency, right? Initially, what happens? Initially, this is also constant. This is also constant. And initially, there is a rise over there. So initially, it will increase, and then it gets saturated. It will be constant, right? So if I add them together, it is something like this. Right? This is the variation. The variation is something, sorry. Yeah. This is the variation. Here I find that at very low frequency, it will increase by 6 dB per octave or 20 dB per decade. Then ultimately, when the frequency operation is very large, then it is becoming constant, and that constant value is given by 20 log mod k. That this one. Because the second parameter, third parameter are cancelled. They will cancel each other, second and third parameter at very high frequency. And this is the frequency of, there is a 3 dB drop from the maximum gain. The maximum gain is 20 log, and over here there is a 3 dB drop. And this particular frequency is known as, last time you have seen that there is a higher cutoff frequency, and this frequency is known as a lower cutoff frequency. We call it f of L. This time the graph, previously the graph was something like that, right? Previously the graph was something like that. This is frequency, this is your gain, right? And this time the graph is like so. This is f, this is your gain in dB. Okay, so here we have got what is known as f of h, the higher cutoff frequency corresponding to a low pass filter, and here we got what is known as the lower cutoff frequency corresponding to a high pass filter. Remember, lower cutoff frequency associated with the high pass filter and higher cutoff frequency associated with the low pass filter, and their difference fh minus fl will give you the bandwidth of the amplifier. Fh minus fl. This bandwidth is given by fh minus fl. This one. Fh typically it is governed by fh because fl is typically very small. Okay. So now let's take some arbitrary value over there, and let's see what is that f. And in order to get this bandwidth, you have to ensure that this fh must be greater than fl. Otherwise, fh minus fl will be negative. That is having no significance, right? So typically, what we get over there, what was that particular thing? This is Rs plus Ri times Cc, right? Rs plus Ri times Cc. Now, typically RS plus RI is governed by RI because RS is typically small. Now, if I consider that okay, this is in the kilo ohm range and let it be say 10 kilo ohms and CC. Now, there is an important issue that how to select the value of CC, this coupling capacitor. What is your job? Your job is to make the lower cutoff frequency as small as possible. Lower cutoff because you have to ensure that the bandwidth is larger. No? So lower cutoff frequency as small as possible and higher cutoff frequency as high as possible. Higher cutoff frequency is essentially governed by those internal capacitors like your C pi and C mu. And lower cutoff frequency is governed by one parameter you have seen, one capacitor you have seen, that is CC. CC will govern the lower cutoff frequency. So accordingly, you have to select the value of CC. What should be your CC value, right? Coupling capacitor value. Now you have to reduce. Now this is already 10 kilo ohms, say for example. Now, so obviously for your internal capacitor, the value was like in the range of picofarad. Picofarad. Now let's take CC to be in the range of microfarad. So obviously it is higher. No, your job is to keep the lower cutoff frequency as small as possible. That means you have to increase the time constant. Time constant and cutoff frequency, they are reciprocal to each other. Tau and F, they are reciprocal to each other. So I have to increase this time constant. I need to increase the time constant, or I have to reduce the lower cutoff frequency. So if I take, say, 1 microfarad, suppose this is equal to 1 microfarad, say for example, if I take it 1 microfarad, then tau is coming out to be 10 millisecond. Right, if it is 10 millisecond, that means what is the frequency then? If it is 10 millisecond, 1 upon twice by tau. Right? If it is 10 millisecond, it is coming approximately to 15 hertz. 15 hertz. Right? Now the question is, if it is 15 hertz, then is it expected? I mean, is it acceptable, this one, or would you like to reduce it further? So it depends on the application. Apparently it is fine for audio amplification because for audio amplifier, you know, for audio amplifier, audible range starts from 20 hertz.
15 has to 90 kilos.
Right. For audio amplifier, audio signals, I mean the audio signal frequency audible range is from 20 hertz to 20 kilohertz. Right. So if it is less than 15 hertz, if it is equal to 15 hertz, that means you are very much within the limit of the audio signal. So it is in the audible range. So it's fine. So you cannot make it so it is in the range of. It is 1 micro, no? With one micro, I've got this. With 1 microfarad. Right. Now, if you can make it say in the range of say picofarad, then what happens? If I select the CC value in the range of picofarad or nanofarad, what happens? In that time, your time constant will be less, so FH will be or FL will be increased. That you don't want. So that's why you'll see that in most of the circuits, electronic circuits, coupling capacitor CC is in the range of microfarad. Not in the range of picofarad, not in the nanofarad. Because the coupling capacitor, you are connecting or you are using this value or you are selecting this value as per your requirement, as per your wish. So accordingly, you have to ensure that this lower cutoff frequency should be for audio amplification should be close to tens of hertz, close to 20 hertz, 15 hertz, 10 hertz, like this. So accordingly, you have to select the value of the coupling capacity. It cannot be in the range of few hundreds of microfarads. You can make it hundreds of microfarad, but if you that will not. I mean, if you with CC is equal to 1 microfarad, you have got like 15 hertz. That is good enough. There is no need to increase it further. So 1 microfarad is good enough. But the caution is that you cannot reduce it, because if you reduce the value of CC, then eventually it will increase the value of your lower cutoff frequency. That you don't want, right? Okay, so that is the effect of the coupling capacitor. Next, we move to the effect of the load capacitor. Load capacitors might be connected over there between the output terminal and the ground, like so. And then once again, if you just observe, so this is pretty simple. The effect of the load capacitor. So I mean, if you have this load capacitor, what is the effect? What is the effect of the load capacitor? What is the behavior of the load capacitor? How does it behave? Will it give you the impact of, now here in this circuit we have incorporated the coupling and load together, right? There we have got the coupling capacitor, here also this coupling capacitor is present. Apart from that, you have the load capacitor is present. Both of them are present. right? Remember, both of them are external capacitors, none of them are internal capacitors, right? So what is the effect of the coupling capacitor? Coupling capacitor is coming in the series path, right? And the load capacitor is coming in the parallel path across this output terminal. So therefore, this one will give you the notion of this thing will give you the notion of high pass filter, this part, and this part will give you the notion of low pass filter, just like you have seen last time. Internal capacitors, right? So load capacitor will be having the other different types of effects. Coupling capacitor will give you, I mean, if I just once again go back to the circuit, this is the effect of the coupling capacitor. What is that? This is a high pass nature. As frequency increases, then the effect of the capacitor will become insignificant. But at low frequency, the capacitor is very much significant. And here the load capacitor is there in that path, I mean, across this output. So the effect is what? Of a low pass filter. So basically, as I've told you, that one circuit is this, right? Input versus output. This one is input, this one is output, and the other circuit is this.
পরেরটা লো পাস, প্রথমেরটা হাই পাস।
This is output, this is input. Right. So this will be nothing but your, this is nothing but your HPF.
হাই পাস আর সেকেন্ডেরটা লো পাস।
And this one is LPF. Right. Now what is that capacitor? This capacitor basically the coupling of the CC. Right? And this capacitor might be the load capacitor, sometimes it is also an internal capacitor. Okay. So once again, sometimes you have to, in your circuit you have to use some load capacitor, and accordingly you need to find out the value of the load capacitor. What should be the value, effective value? Because you have to ensure that that should not interfere with that. Already have got some frequency, na? The high frequency, I mean the higher cutoff frequency have got some 20 megahertz, you've got some value. So accordingly, so here what I find, this higher cutoff frequency is given by 1 by twice by tau h. But tau h, what is that tau h? What is that tau h? This one. What is that tau h?
Time period of the
Time period of the RC circuit. What is that? Typically this is RC RL parallel combination and multiplied with CL. Typically this RC and RL, typically they are in the range of kilo ohms.
সিএল খুব ছোট হতে হবে।
Typically they are in the range of kilo ohms, right? So typically
সিএল বড় হয় না,
সিএল ছোট হতে হবে কারণ টাওটা তো কমাতে হবে, আমাদের ফ্রিকোয়েন্সি বাড়াতে হবে।
তো আরসি আছে।
last time I noticed that for your high pass filter, high pass response, the time constant is in the range of milliseconds. And last day, if you can remember, the time constant was in the range of nanoseconds. Time constant was in the range of nanoseconds.
Frequency to megahertz.
Right, megahertz, tens of megahertz. So there also you have to ensure that, because remember this, whenever you connect some load capacitor, so response is something like this. Whenever you connect some load capacitor, the response is something like this. So that frequency, this frequency, if I call this frequency, let it be say f of h, that should, I mean, you have to keep it at a very high range. That means what your tau should be small, right? So you don't have any control. Okay, this RCRL is in the typically is in the range of kilo ohms, because you know some gain constant is there, GMRC and all. So this is in the range of kilo ohms. So you have to reduce this tau which you have to reduce. So you have to reduce the value of CL, right? So typically, so you have to keep it in the range of nanosecond, because RC is in the range of kilo, 10 to the power 3, and if you can keep it in the range of, the product is in the range of nano, that means what? 10 to the minus 9. Nano is 10 to the minus 9. So there is something 10 to the power 3 multiplied with something that will give 10 to the minus 9. So that thing C should be in the range of pico. Right? You have already observed that for internal capacitor that was in the range of picofarad, 11 picofarad, 1.5 picofarad. So there also I take CL in picofarad. Then picofarad multiplied with kilo ohms, that will give you, the product is in nanosecond. Now if it is in nanosecond, that means hundreds of megahertz. That means it will not interfere. But if you select some CL in the range of say 100 or 1 microfarad, what happens then? Just like your coupling capacitor. Just like coupling capacitor, if you select the CL in the range of microfarad, then what happens? That means this time, if had this been the case, that means CL is also in the range of say microfarads or 100 or say microfarads or in that particular range, or in nanofarad also, say for example nanofarad, then what happens? Nanofarad means 10 to the minus 9 multiplied with 10 to the 3 will give 10 to the minus 6 microsecond, right? Then ultimately this, because of CL, the bandwidth will be in the range of few tens of kilohertz or hundreds of kilohertz. It cannot move towards megahertz. That means in that case the CL will interfere with the high frequency response that you don't want. So that's why typically the CL value to be in the range of picofarads. While CC is in the range of microfarad, but CL should be in the range of picofarad. So that you have to ensure that this FH must be much higher as compared to the FL value, so that this FH minus FL is a commendable one, and that should be greater than 0. Okay, so still one part is left, only one, because we have encountered everything. There is the coupling and the load, only one is left, that is bypass. So bypass capacitor is a very tricky one. So okay, we have to go for once again the small signal model for this bypass capacitor, and hopefully that part is well known to you, how to draw the small signal model and all. This one is well known to you, and we are interested in finding out the frequency, the transfer function part. How does it look like? Okay, so if we just do this calculation, then ultimately what I am getting, this is nothing to worry about. You have to only apply this KCL and KVL. Alright, and then ultimately what I am getting is this part. Don't get afraid with this calculation. It is basically the way you do this KCL and KVL, you analyze the loops and all. Then ultimately, let's find out the final expression. What I am getting. So this is the final expression over there, and out of this part is the constant parameter, right? Gm r pi rc upon rs plus r pi plus 1 plus beta times r. That's great. Okay. And then apart from that, now you have this thing. This is a frequency dependent parameter, 1 plus SREC divided by this entire thing. So this can be represented in this form, k into 1 plus S tau 1 divided by 1 plus S tau 2. So therefore you have two different time constants. Although you have only one bypass capacitor, but since it is connected in that particular fashion, this bypass capacitor is connected between the emitter terminal and the ground. So accordingly, if you perform this circuit analysis, then we get two different time constant. One time constant is obviously, you understand, 1 plus S REC, right? 1 plus S REC. So what is the time constant? Tau. REC is the time constant. Second time constant is how much? This one, REC multiplied with RS plus R pi divided by this entire thing. Okay. So I have identified two time constant. One time constant is tau 1, this much. Second time constant is tau 2, this much. But what will be the effect? I mean, if I draw this one now, k into 1 plus S tau 1 by 1 plus S tau 2. Already you notice how to, what is the effect of k by 1 plus S tau? You know, the low pass response. As frequency increases, gain drops. K by 1 plus S tau. There is no S parameter in the numerator. This is there in the denominator. So as frequency increases, this drops. But now here you have this S parameter both in the numerator as well as this S parameter is in the denominator. So therefore, to observe the behavior of this kind of frequency response or transfer function, what I need to observe, I have to observe this frequency response from two different extreme points, at very low frequency and at very high frequency, right? At very low frequency means what? At zero frequency. When omega equal to 0, what will be the value of this AP? Again, that is simply k, right? And when omega is, suppose it is infinite, very large, then what will be that value? This is nothing but tau 1 by tau 2 multiplied with k, because if you divide this expression by 1 upon s, so 1 upon s plus tau 1 by 1 upon s plus tau 2, at very high frequency 1 upon s is becoming close to 0. So k tau 1 by tau 2. So one time you find k, and second time you find k into tau 1 by tau 2. So, to ensure that, ultimately what is your job? Your job is to design some amplifier, right? At very low frequency, at DC frequency, very low frequency, the gain is k, the value is k, right? And when the frequency operation is very large, it is k into tau 1 by tau 2. So you have to ensure that this tau 1 by tau 2, this part should be greater than 1, right? And that is already validated over there. Why? Because tau 1 is given by RE times C, and tau 2 is given by this one, RE times C multiplied with this. And obviously this factor is less than 1. This one, isn't it? Because rs plus r5 is in the numerator and the denominator you have rs plus r5 plus something. So therefore tau2 is less, tau1 is more. Okay, so therefore since tau2 is less, tau1 is more, so at omega to infinity, that expression of the voltage gain is greater than the voltage gain at low frequency or zero frequency. Okay, so therefore if you just so there are basically two different corner frequency, one corresponding to your tau1 time constant, second one corresponding to your tau2 time constant. There are two corner frequencies because you have the expression in the form k into 1 plus s tau1 by 1 plus s tau2. Then it looks something like this. You have two corner frequency. This is the response, right? This is the response. This is f1 corresponding to the tau1. Tau1, which one is larger? Tau1 is larger, so f1 should be smaller, and tau2 is small. Tau2 is smaller, so f2 should be larger. Okay. So once again, it's a high pass response. It's a high pass response. Now, since it's a high pass response, you should not bother about the higher part, because at very high frequency it will give you a constant value. But you should be very much aware about this lower cutoff frequency. This one. This should not be. I mean, at least this should be at least your 15 hertz or 20 hertz. Right? It cannot be 50 hertz or 100 hertz. Because in that case, if it is like 50 hertz or 100 hertz, in that case, it will severely affect the low frequency response of the amplifier. How to ensure this? How to ensure that this is small enough? This is at least 10 to 15 hertz, 20 hertz, not at least 100 hertz. What is the condition that you have to maintain? Yes. So accordingly, you have to select the value of this one, this REC combination. Typically, what I know, typically your RS is okay, RS 50 ohms, R pi you know, that is 5 kilo ohms. RE typically we consider RE is equal to 1 kilo ohms. Say 1 kilo ohms RE. Had this been the case, then and if I consider C to be 1 microfarad, for example, then what I am getting tau1 to be 1 millisecond, tau2 to be 0.048 millisecond. So then your F1 value is coming out to be 150 hertz. F1 is 150 hertz. Is it allowable? No. 150 hertz with RE is equal to 1 kilo ohms and C to be 1 microfarad. It is not allowable. 150 hertz, that means although with coupling capacitor the effect was like from 10 hertz onwards, but here it is 150 hertz. 15 hertz onwards, it is that means 10 times more. So that means this particular, because of the inclusion of this bypass capacitor, it is severely degrading the low frequency response. That you don't want.
Sir, বলছি এখানে যদি আমি এক কাজ করি আর এর ভ্যালুটা যদি বাড়াই তাহলে তো একটা করা যায়।
Okay, you can increase RE, but there is something to deal with the gain also, because for this kind of amplifier, you can remember the expression for the voltage gain was like RC upon RE, right? If you increase RE, then the gain will be compromised. Forget the minus, it's RC upon RE. So if you increase the RE value, it will be compromised. The gain will be compromised, because you know every time the gain bandwidth product, you know, every time will hurt about this one. So you cannot reduce, you cannot increase RE as per your requirement, right? Because if you increase RE, the gain will drop, gain will fall. So only one option left. So initially I started with 1 microfarad. That 1 microfarad with the coupling capacitor, right? Coupling capacitor 1 microfarad, there also 1 microfarad.
1 millifarad.
Right? So what I need to do? I have to reduce F1, so I have to increase. I have to increase this tau. I have to increase tau. So don't take it 1 micro, rather take it some hundreds of micro. Right? Hundreds of micro. Let's take 220 microfarad. Let's take 220 microfarad, right? With 220 microfarad, now you find that F1 is coming to 1 hertz only. Now you are happy. 1 hertz, that's great. And F2 is equal to 15 hertz, that's great. Because beyond 15 hertz, okay, that means what? The response is something like this. Because of this bypass, this is say 1 hertz, and this high frequency is at 15 hertz.
স্যার এখানে একটা জিনিস প্রশ্ন, সেটা হলো একটুটা তো অনেক কমে আছে। হ্যাঁ তো
No problem at all. Beyond F2, everything is constant. Beyond F2, everything is constant. Beyond F2, the gain is constant, right? So if I select the C to be in the range of hundreds of microfarads, let it be 220 microfarad, then this behavior will not affect the frequency, low frequency response of the circuit. Right? So in exam you'll find that the questions are coming like this: why the coupling capacitors are taken in the range of microfarad? Why the bypass capacitors are taken in the range of hundreds of microfarads? Why the load capacitors are taken in the range of picofarads? Why not the other way around? These are the reasons. These are the reasons. Why so? Why so? Why you cannot afford to take C in the range of picofarad? Why you cannot afford to take the CC in the range of picofarad? Why you cannot afford to take the CL in the range of microfarad?
So calculation for another.
At least you have to provide some information regarding.
No,
Okay. Okay, I think with this we have ultimately come to the end of this course on electronic circuits with this behavior of this frequency response, and with this let me conclude.